we want to study so-called the complete integral. Okay, so what is the complete integral for that? So you consider a parameter set A, which is a subset of R2 because we are in a two independent variable x and y. So A is a subset of R2, which we denote as a parameter set. And we define this matrix DAU and DX square U, which is nothing but the matrix that UA1, UXA1, UYA1, then UA2, UXA2, and UYA2. So now we say that, say UXA, X means here in this case X and Y, A is A1 and A2, something like that. It's said to be a complete integral in the domain say U cross A of your nonlinear PDE, capital F of X, Y, U, Ux, Uy is equal to 0 in the domain U, is it not? So if this U satisfies your PDE, and another conditions I need that the rank of my matrix DAU and DX square U, that should be equal to 2. Okay, so for that we are finding the complete integral of your nonlinear PDE. So our goal is to find out the general solutions for nonlinear PDE. So we have done it, the general solution for quasi-linear PDE, but for nonlinear PDE it's a little bit complicated. So for that we need these kind of preparations. So now we study how to build more complicated solution for the nonlinear first order PDE. So for that we need to construct so-called the envelope of a family, or in particular I'll define so-called the singular solution. So let me define as the envelope of the family. So this is envelope of a family. So what it says that, now suppose your U is a integral solution, sorry, the complete integral. So that means U, X, Y, say A1 and A2. This is C1 function on U cross A, where A is your parameter set and U is an open subset of R2. Now, if I can find out my parameter A1 and A2 from this equation, okay, so that means if this can be solved so that I have a solution A1 is equal to say some phi of xy and A2 is equal to some psi of xy, that means that is dou u dou ai of xy phi of xy psi of xy is equal to 0. Then we call, if we define v of xy, which is u of xy then a1, now it is a solution which is phi of xy, a2 which is a solution now psi of xy. This function v is called the envelope of the functions this u dot and a. Okay, where a is in my parameter set. So what it says that envelope of the envelope of a family of your solution UA, what it says that you need U, it should be your complete integral, that is why ux u1 a2 it's on because A, and now this a1 and a2 I can determine from this equation dou u dou y xy a1 a2 is equal to 0, so it can be solved. That means I have a1 which is a function of xy and a2 which is a function of xy, which is a psi of xy. Now if I define vxy, which is u xy, phi of xy and psi of xy, then this function v, it is a envelope of the family of u dot a. So now whether this v is a solutions or not, that is actually we need to confirm it. And actually it is a solution to your first order nonlinear PDE, and this v we will declare it as called the singular solution. So let us see whether v it solves my nonlinear PDE or not. So now suppose for each say a1, a2 in my parameter set, u, which is u a1 and a2, which solves my first order nonlinear PDE, which is f of x, y, ux, uy, which is 0. Now assume that the envelope v, which is defined above, is exist and C1. Envelope B exists and C1, then claim is that this envelope V, it also satisfies my first order nonlinear PDE. Then Vxy solves the nonlinear PDE. Okay, first order nonlinear PDE, which is f of x, y, u, ux, uy is equal to 0. Okay, so this envelope, what it says that basically envelope also satisfy your first order PDE. How to check it? If I show that my ux is equal to v of x, the partial derivative with respect to ux, which is same as the partial derivative with respect to vx, then we are done. So basically what I have, since v is a envelope, that means I have v of xy, which is u of xy some function phi of xy and then another some function psi of xy. Is it not? So now u is a solution to your means u, which is this one, u dot a1 a2, which solves your first order PDE. So from these assumptions, what I have, f of xy, u xy, p xy, psi xy, then ux of xy, p xy, psi xy, then uy of xy, p xy, psi xy, this is 0. Is it not? Because what it says that u is a complete u dot a1 a2, which is a complete integral. That means I have this part. Because of the existence of my envelope v, I know that a1 is a function of phi of psi xy for some function p, and that can be solved using your that equation dou u dou ai of xy a1 a2 is equal to 0. So now since my v is c1, what I have vx of xy. So if you look at this is ux of xy p xy psi over xy, then plus dou u dou a1 xy p of xy psi of xy, and then px of xy plus dou u dou a2 now xy. Okay, then p of xy psi of xy, and then you have a psi x of xy. So now this quantity dou u dou a1 xy p xy psi xy is equal to 0. Similarly, this part is also 0 because v is a envelope, and what I know that a1 and a2 can be solved from that equation by the definitions. Dou u dou ai xy a1 a2 is equal to 0. That means a is equal to some function of xy, a2 is equal to some function of x of y. So what you have, what you end up with, v of x is equal to my this part. Similarly, So v of xy, which is nothing but ux of xy pxy psi of xy. And similarly, what I can have vy of xy, which is uy of xy p of xy and then psi of xy. So now since my f satisfies these things, because u is a complete integral with respect to the parameter a1 and a2, then what I have that v xy solves the PDE. Okay, so this solution V, now the envelope of your family, it solves your first order PDE. This V is called the singular solution. So I put as a definition that the solution V is called a singular solution of the nonlinear first order PDE, which is f xy u ux uy, which is equal to 0. Okay, so let us consider one example how to find out a singular solution. So to find out the singular solution, you have two parts. First part is, okay, you try to find out the complete integral. Already we know how to find out the complete integral. So to find out the complete integral, you need to find out two functions, say phi xyz and psi xyz, which are constant along the characteristic equation. Is it not? And so on. Okay, so what I have here, I am considering this nonlinear equation ux square plus uy square, which is equal to 1 plus 2 of u. Okay, I want to find singular solution. Okay, so for that, as I said, that it is two step. First, you need to find out the complete integral of your given PDE. So for that, what you need to find out, what is your, in this case, what is your f of x, y, z, p and q. If you write down, this is p square plus q square minus 1 minus 2 of z. Is it not? So that is why f of x, y, z, p, q, it gives you 0. Okay. So from here, what is the characteristic equation now? I can have this is dx dt, which is fp, no? F of p means partial derivative with respect to p, that should be your 2p. So what is your dy dt? Again, that is f of q, this is 2q. And then what is your dp dt? That per no, minus f of x minus f of z and then p. So from there you see that here it should be your 2 times p. And what is your dq dt? This is your 2 of q. Okay. So now if you solve these things, what we have, p is equal to c1 times e to the power 2t, q is equal to c2 times e to the power 2t. And hence from here what I have, p by q, this is c1 by c2, so I can think of p by q is equal to some another constant, say a. So hence I have p by q, which is some a. Okay, because c1 by c2 I have, so this is a. So now from the equation what I have, p square plus q square minus 1 minus 2z is equal to 0. This is your given equation because f of x, y, z, p, q is equal to 0. From there I have this is equal to 0. So for that case what I have, P should be plus minus A times root over of 1 plus 2z by 1 plus a square. Is it not? Because you just put P is equal to Q times A, or maybe Q is equal to P by A. So from there you solve these things. Okay. And similarly, I have my Q. So as long as you know P, so Q should be P by A. So then it should be, okay, which one I have written down? So this is 1 plus 2z. So a square Q, then it should be Q, no? Because if you take common Q, 1 plus a square, 1 plus a square I have. Okay, so then Q should be root over of plus minus 1 plus 2z by 1 plus a square. Is it not? This is my Q, and then this is your P. So now what is your strip condition? I have on the strip condition which is dz dt, which is P dx dt plus Q dy of dt. This is my strip condition. So from there what I have, this is nothing but P is plus minus A root over of 1 plus 2z by 1 plus a square dx dt, and then this is plus minus root over of 1 plus 2z by 1 plus a square, which is dy by dt. So these things actually I can write down. This is plus minus root over of 1 plus 2z by 1 plus a square, and then a dx dt plus dy by dt. And now if you integrate it, okay, then what you have from here, that root over of 1 plus 2z, this is equal to plus minus ax plus y by root over of 1 plus a square, and then plus b. Okay, hence what I have, because z is there, so I want to have u. So if I define u, x, y, a and b, so from here actually, because z is equal to your u, so from there I have, this is half of ax plus y by root over of 1 plus a square plus b whole square, means you take that whole square. Okay, you take this whole square, and then you take 1, so half, that's I have minus of half. Okay, so this is a complete integral. If I say, if I check that the corresponding rank of that matrix, so now u, x, y, a, b, which satisfy your PDE. Okay, so now to find out the complete integral, what I have to check it, that the rank of this matrix dAu dx square of u, this should be 2. Okay, so you check it, that just find out the matrix dA of u, because you have now this form, you can find out, and then you see that actually the rank is 2. Hence u, x, y, a and b is a complete integral of your given PDE. Okay, so now if you try to find out your envelope, so for that you need to eliminate your a, b from the equation, that u of a is equal to 0 and u of b is equal to 0. So now you check that u a is equal to 0, ub is equal to 0. This gives ax plus y by root over of 1 plus a square plus b is equal to 0. Okay, hence, so that means basically I need to eliminate my parameter a and b, which solves your this equation ua is equal to 0 and ub is equal to 0. So that gives actually x plus y root over 1 plus a square plus b is equal to 0 in this form. So here again in a implicit form, but still for this problem it is okay because u of xy ab is equal to in this form. So if I define my v of xy, which is now this one is equal to 0, so I have minus half. Okay, so hence vxy, which is half, is a singular solution of the given PD. Okay, so what is the work methodology? To find out the singular solutions of a given nonlinear first order PDE, first you have to find out a complete integral. Okay, and then you try to solve the parameter from the equation, which is dou u dou a is equal to 0 and dou u dou b is equal to 0. From there you try to solve a and b in terms of some function of x and y, and you define your v of xy, which is u xy and then say phi of xy psi of xy. That v is a singular solution to your given PD. Okay. So now I have a singular solution. So now I try to define so-called the general integral. Okay. So for that, what I need, so I consider A, which is a subset of R2, the parameter set. So I can have something like that if I have, say, open set A, which is a subset of R2, sorry, R, okay, and suppose I have a C1 function A, which is from, say, A tilde to R, which is C1, such that my graph, if I look at my graph, say A tilde and H of A tilde, if it is lies in my set A. Okay, so the graph lies in my parameter set A. Now I try to find out the functions with respect to my A or A tilde. So I'm defining. So now depending on your age, no, so there exists one function such that these things. So depending on your age, you may have a different general integral. So what is say that the general integral, which depending on my function age, which is the envelope, I denote v tilde of xy of the functions. So now I put as a u dot a tilde, where my a tilde is a tilde. Okay, provides the envelope which should exist, then I can talk about and C1. And what is your this function? U dot x y say a tilde. This is nothing but I have u x y. This is the short notation a tilde and then h of a tilde. So now initially you have a two parameter, no, a and b. So now my b is a function of a. So that's why I put it a tilde h of a tilde, such that the graph which is a tilde h of a tilde lies in my parameter set a. Okay. So general integral is again kind of your singular solutions, but here you have a one parameter. Let us consider one example. So find the general solution. Ux uy, which is equal to u. Okay, so already we have seen that the complete integral. So complete integral already we have find out, no, u of x, y, a and b which already we had x minus a times y minus b. Okay, so now I try to find out my h, which is a function from r to r. So complete the general integral, it depends on your function h. So I am define h from r to r such that h of a, which is equal to a. Okay, so what I have then, if I define then u of x, y, a, this gives you x minus a times y minus a, and hence ua is equal to 0. This gives my a, which is equal to x plus y by 2. Is it not? So then what is the general solution? So the general solution or the general integral, in this case what it will be? I define v of xy, which should be actually u of x, y, and then your a, which if you define it here, u of x, y, a. So now if you look at here, so x minus a, and yeah, from here x minus a and then y minus of a, and a is actually your x plus y by 2. So from here what you have, this is nothing but your minus x minus y by 2 whole square, is it not? Because x minus a, if you look at, and then y minus a, so from there you have minus of x minus y square. Okay, so for the singular integral, you have to eliminate your parameter a and b, but here only thing is that I have to eliminate only one, because the another parameter is a function of h, so that is in your hand. Okay, so in this example, I'm considering h of a is equal to a, looking at how these things looks like, and then I have this part. Okay. Let us consider one more example, and then I'll stop this first order PDE, and then I'll talk about the second order PDE. So what is the general integral of ut plus ux square is equal to 0? Okay. So you check that uxt a and b. Okay, so maybe you can think of y, whatever you want. Okay, you put as t is equal to y, where y is positive only. So uxtab, this is ax minus t of a square plus b is a complete integral. Okay, you check that it is a complete integral. So now I am considering that function h from r to r such that my h of a, which is equal to a square. So then what is my u x t and a? This should be nothing but your ax minus t square plus a square. Then u of a is equal to 0 gives a is equal to x by 2 times t minus 1. So what is the general integral? Thus general integral is, if I denote as a v of xy, this should be, what is your u? You put the value of a here, so this is what it will be. Okay, you just check it. This is a means x by 2 times t minus 1 x square minus t into s square. So x square by 2 into t minus 1 whole square, and then plus s square. So I can have t minus 1. Is it not? So whatever you have from here, so this is 1 by 4 half. So I have half of, or 1 by 4 of t minus 1 times x square. Is it not? Because here you have 4. So just see, maybe 4 half, 1 by 4 maybe. Yeah. So this is x square by t minus 1. So the general solution to this equation ut plus ux square is equal to 0 is x square by 4 of t minus 1. Okay. Okay, so I'll stop this first order PDE. So in the first order PDE, what we have learned so far, first we classify the type of PDE in the sense that whether it is a linear, whether it is a semi-linear, whether it is a quasi-linear, or it is a non-linear PDE, the fully non-linear PDE. And then we have seen that, okay, given how to solve quasi-linear PDE, so for that, we have used so-called the method of characteristics. What is your method of characteristics? It is basically the method where I try to that PD you are just projecting on your plane so that it gives you a system of ODE and then you try to solve it. So for that I need to parameterize my initial curve as well as the integral surface, because finding out the solutions to your given quasi-linear PD, which is equivalent to finding out the integral surface. Okay, and integral surface is nothing but the smooth union of your integral curves. So the integral curves is coming to solve this system of ODE. Okay, and then you have seen that, okay, so this can be solvable under the assumption of the coefficient, suppose it is in C1 at t is equal to nearby t is equal to 0. So for that, what we have now, we have x and t and x and y and then t and s. So you need to convert it because our equation is in terms of independent variable x and y. So for that case, you need to use the inverse function theorem near t is equal to 0. So that is possible if the initial curve gamma is non-characteristic. Is it not? So that I think a prime s minus b or b a prime s minus a g prime s is not equal to 0. Okay. So for the non-characteristic curve, one can solve uniquely the quasi-linear PDE in a neighborhood of the initial curve. Okay. So always the method of characteristic gives the local solution, not the global solution. Okay. It's always the local solution. Okay. So then how to solve it for your first order nonlinear PDE? So just taking from the motivations from your quasi-linear PDE, what we are doing, we try to again construct so-called the characteristic strip, so which involve the equation for P and Q. What is your P? P is nothing but the U of X and Q is nothing but U of Y. Okay, the partial derivative of U of with respect to X and with respect to Y. And from there, we try to find out the characteristic speed. So to solve that, I need two more initial conditions. So for that, what we are using, that I need the admissibility conditions and that h of s, which is the initial parameter for gamma, that should be u of fsgs, and from there we deduce p0 and q0. Is it not? So you see that we can have infinitely many p0 and q0. So as long as your p0 and q0 is fixed, initial condition is fixed, we can have a solution which is unique for your nonlinear first order PDE. Okay, so then we try to find out so-called the general integral. So for the first step is to find out the complete integral. So complete integral means basically I want to have a parameter set A, and then we need to check whether uxs solves your given PD or not. Okay, so that is actually we have solved it. and then we need to define so-called the envelope. Okay, so what is your envelope of your envelope or the singular solutions if you're given nonlinear PDE? Rohit, would you please mute yourself?
Yes, sir. Yes, sir. Okay.
Then what happened that you have a singular PDE, that means you need to find the complete integral and then you try to solve your parameter A1 and A2 from the equations dou u dou I is equal to 0. Okay, suppose you have a solutions for that. So A1 is equal to phi of xy and A2 is equal to psi of xy. Then if you define v of xy which is equal to u of xy, phi of xy, psi of xy, that is called the singular solution. Okay. And what is your integral, general integral? So I have two parameter set, but I want to have only one parameter set. So for that, I'm considering one, say, open subset of R. Okay, and I look at the function h, which is a C1 function, such that the graph of this h, in particular a tilde, h of a tilde, is lies on your parameter set. Okay, and so then the general solution is depending on your h. So there you have initially you have a, for the singular solution you have a two family of parameter, the two parameter family, but here I have only one parameter family. Okay, and then you find out the general integral. Okay, so now I will talk about so-called the second order PDE in again in two independent variable. Okay, so next chapter is second order PDE is in two independent variables. So basically it looks in this form a x y u ux uy uxx, okay, plus maybe I put as a 2b, again b is a function of x y u ux uy of u xy, plus maybe c, again it should be a function of x y u ux uy of u yy. Is it no? This is your second order kind of quasi-linear type, no?
So why we have put 2b, right?
I just put it for simplicity, nothing else. You can put some b. Okay, this is just for the means for the simplicity means actually later on actually we'll have some formulation, so there it is easy to remember.
Okay, sir.
Okay, like in your whenever you consider say second order in x and y variable. Okay, second order equation. What I wrote down that ax square plus 2bxy plus c square is equal to 0, so that if you look at that b square minus 4ac, whether it is positive, negative, and so on, no, that is you have done it for you in your I think 12th class or something like that, just for the easier things to write down. Okay, you can put only b, no problem. Okay, so this is form, and then d of x y u ux and uy. So you see that it is a quasi-linear PDE, but second order. Okay, it is a quasi-linear PDE, but second order. So again, what is the quasi problem in this case? We want to find u which satisfies my this equation 1. Okay, with given values of u ux and uy on a given curve. Okay, so I have a given curve gamma, small gamma, which is in the xy plane. So here if I know the value of say ux and uy, it is given to u, and in Cauchy problem corresponding to the second order Cauchy linear PDE means actually we want to find a solution u which is function of x and y which satisfy equation 2 such that automatically we know that ux uy on a given curve gamma on the xy plane. Okay, exactly in a similar way. So now if you parameterize your gamma, which is say fs and g of s, so then you can prescribe the Cauchy data, which is u is equal to say h of s, and u of x is equal to say some p of s, and u of y, which is equal to psi of s. Okay. So in general, the Cauchy data along the gamma. Okay, here I am only giving you say solution u and then the partial derivative ux and uy on this given gamma. Okay, but in general, what it says that the Cauchy data along gamma, it is of this form: u on gamma, it may be h. So not only this partial derivative, it may give you the Neumann condition. So I just first wrote down dou u dou eta over gamma, that is my h1. So what is your eta? Eta denotes the unit normal vector along gamma, always the outward normal. Unit normal vector along gamma. So how do you define this dou u dou eta? This is grad u dot eta. Okay. So now that is why even if that grad u dot eta, so that means basically again it is in terms of x and y. So for simplicity, we are just considering that ux and uy is known along gamma. Okay. So now suppose the values of any function v, okay, and its partial derivatives say vx and vy along my curve gamma, which are connected by the stripped condition. That means dv d of s, which is my v of x f prime of s plus v of y of g prime of s. Okay. So what I'm saying that any values, the values of any function v and its first order partial derivatives, say vx and vy along the gamma, these are connected by this equation. Okay. So how to find out these things actually? Because if you differentiate my function v of fs and gs with respect to s, then we have this is h prime of s, which is equal to phi of s f prime of s. So differentiating v of fs and gs with respect to s, what I have h prime of s, which is my phi of s, because you okay, so if I denote that v is given to u on the gamma, okay, here I put as a u, but you can think of for any function v such that the partial derivative, okay, first order partial derivative is given to you on along the gamma, whose parameterization is basically hs, phi s and psi of s. So from there what I have h prime of s. Second.
So can you again explain what is v?
Say.
So what is v? What is v here?
What is v here? You are saying?
In this function v that we are
No. What I'm saying that I have my curve gamma. Okay, and suppose my function v, any function v, it may not be u. Okay, any function v which is known or which is given or along my curve gamma. Okay, so basically you can think of v is my u now. You can think of v is my u now. So what I'm saying here that along my curve given gamma, I know the functional value and then the first derivative, okay, which is v of x and v of y. And gamma actually I am parameterize it by v which is my h of s, and then the partial derivative I have which is phi of s and then psi of s. So then the v, how it is connected, that if you look at the total derivative with respect to s, so dv ds, this should be nothing but that v of x f prime s plus v of y of g prime of s. So now if your v of s is equal to h of s, so now if you differentiate it, v of fs and g of s, because now the x coordinate is f of s, y coordinate is now g of s. Okay, so if the initial condition means on gamma, v is given to which is by h of s. So from here what I have h prime s, because it is connected through these equations, no? The values of v and then the partial derivative, first partial derivative, it is connected along gamma by this compatibility condition. Okay. So that is why I try to write down that h prime of s, what I have, this is phi of s and then f prime of s, just like here. Yeah. So in this case, v of x is basically phi of s, because along these things I have given, and then this is the parameterization. Okay. So you can think of, see, u is given to you. I want to solve this PD and so on. So I try to find out again kind of the characteristic condition, non-characteristic condition, whatever I have done it for your first order PDE case. Okay. So here what it is given to you that I have again the initial curve. I try to parameterize your initial curve. So in this case, on the initial curve, I know the first order partial derivative. Okay, so that parameterizations I wrote down as a that u of x, which is my phi of s, u of y, which is a parameterization is psi of s. Okay, so like there are what we wrote down that z of s is equal to h of s, and then we differentiate. Is it not? So exactly same thing else actually I am doing here. So here now v is any arbitrary functions such that it is given to you v and then the partial derivative vx, partial derivative v of y, it is given to you on your gamma. Now I have a parameterization of my gamma which I wrote down. Okay, which is f of s and g of s, and v of x I have a parameterization that is basically my phi of s and then psi of s. This one, phi of s and psi of s. So that is why I try to write down that from the compatibility condition, if I write down which is h prime of s, because v is now h prime of s is equal to phi of s, f prime of s, and then plus I have psi of s and then g prime of s. Okay. So now if you take, say, v is equal to ux, and v is equal to u of y, then what you have? If you take, say, v is equal to u of x and v is equal to u of y, what I have d of ux of ds, which it should be v of x f prime s, so which is u of xxs f prime of s plus u of y, so I have u of xy of g prime of s. Okay, and then I have d of, if you take v is equal to u of y, what I have d of uy of d of s, which is equal to u of xy of f prime s plus u of y of g prime of s. Okay. So now if your u, which is a solution to your given PDE1, the second order Cauchy-Linear PDE, then what I have? Then I have A of uxx plus 2b uxy plus c of uyy, which is equal to d. Okay. And from here, what I have? So what is dux d of s? So u of x is equal to phi of s, and now suppose phi is your smooth again smooth function. So what I can write down? This is f prime of uxx plus g prime of uxy plus 0 times I can put as a this is my phi prime, and from that second conditions what I have, that 0 times uxx plus f prime of uxy plus g prime of uyy, which is equal to my psi prime. Okay, so thus this uxx, uxy and uyy, it will be uniquely determined. Okay, can be determined uniquely because you can write down in a matrix form, no? So the coefficient matrix is now A, 2B, C, F prime, G prime, 0, and so on. So if this determinant is non-zero, if that I put it, the determinant of these things, which I wrote down as a F prime, G prime, 0, 0, F prime, G prime, A, 2B, and C. Okay, this is non-zero. That is what I have, A times G prime square minus 2B F prime G prime plus C over F prime square, which is not equal to 0. Okay, so in first order PDE, we try to also find out that non-characteristic condition. So here actually we are declared it as a non-characteristic curve. So definition. So what I have, that the initial curve gamma is called characteristic again with respect to the differential operator and the given data if my this gamma is equal to 0 here, the determinant which is 0. Otherwise it is called the so it is called non-characteristic if gamma is not equal to 0 along gamma. So that means for a non-characteristic curve, I can determine the Cauchy data uniquely if the second derivative of u, okay, on gamma. So for a non-characteristic curve, one can uniquely determine the second derivative of u on gamma. Moreover, one can obtain the higher derivatives of u along gamma. So that I'll not describe it. But what it says that if gamma is non-characteristic, that means if this condition is hold, so similarly that means it is the case. So one can determine the second order partial derivative of u uniquely. Okay, so I'll stop now and then I'll talk about so-called the normal forms and for all these things that is actually required.